Well, hello again, everybody. We're going to be moving a little bit further along in our notes today, so if anybody missed it in class, this is the notes that we're going to be doing, and it's not very much in terms of actual notes. We're only doing 1 or 2 slides, but the concept is something that we're going to probably need to practice. So we've just gotten done adding vectors graphically. That means that you have vector A right here and vector B right here, which means the resultant vector C goes from the origin to the end of B, if A plus B equals C. Okay, we've done that. We did that up to last week, and we even had a homework quiz on it. But today what we're going to do is we're going to start adding vectors mathematically, or what we're going to call the component method. What that means is that we take every vector, say vector A right here, vector A, and we resolve it into its components. Now by component I mean its X component and its Y component. So I'm going to write them in black here. So we have AX, which should be horizontal. Sorry, I just hit the microphone there. Okay, there's A on the X-axis, and here's AY on the Y-axis. Now these are scalars. These are just values on the X or Y-axis, but they combine to create the vector A. But like I said, if we have vector A, we can break it down into AX and AY. How do we do that? How do we find what AX is right here? Well, we need to know the original direction. Oops, sorry about that. I'm changing to red here. We need to know the original direction of A, and we know that by the fact that it's some degrees. We'll call theta degrees off the horizontal. Again, off the horizontal, not off the vertical. What we do then to find AX and AY is simply use a trig function to find what AX and AY are. So if see, we have this angle right here, so let's solve for AX first. All right, so A, what's the X component of A? Well, that's the adjacent side to the angle, and if we know what the vector A is, we should be able to solve for that because we should know what the angle is as well. Let me write this out so it makes more sense. So we have the adjacent and the hypotenuse. Okay, so A and H, which sine function is that? That sounds like cosine to me. So that means the cosine of that angle, because it's adjacent to that angle, is C is A over H, adjacent over hypotenuse, so that's AX over the hypotenuse, which is our vector A. I should have written AX in black, I guess. But let's now just solve for AX. So the X component of A is simply, if we bring the vector A up next to the cosine, is the vector times the cosine of the angle as measured from the horizontal. To solve for AY, we're going to use the sine. Why? Because AY is the opposite, and sine is opposite over hypotenuse. So the sine of theta equals the opposite of that angle, which is AY, over the hypotenuse A. Which means then to solve for AY, that's simply the vector times the sine of that angle as measured from the horizontal. So we can take any vector, as long as we know its magnitude and its direction, that is its direction based off the horizontal, and break it down into AX and AY, or BX and BY, or ZX and ZY for that matter. We're simply breaking it down to its horizontal and vertical components. Well, why do we care about doing that? Well, because if we want to add multiple vectors together, we can add all their components, all their X components and all their Y components together, and find out the X and Y component of the resultant vector without having to draw anything. Here's what I mean by that.